We all know that the sun powers life on Earth, but what if I told you that the sun was also responsible for radiation storms, GPS glitches, and even blackouts? Today we're diving into one of NASA's most ambitious missions to understand how the sun affects our planet and the solar system. I'm Ben, this is Physics or Bust. Meet Punch, the polarimeter to unify the corona and heliosphere. Punch isn't just one satellite. It's a squadron of 4 microsatellites that'll work together to solve one of the sun's greatest mysteries. How the blazing solar corona transforms into the vast solar wind that flows across our solar system, creating the heliosphere that pushes against the interstellar medium. These tiny satellites have launched into low Earth orbit and operate as a team using specialized polarizing cameras to image the sun's atmosphere in incredible detail, something that's never been done at this scale. The sun doesn't just shine light, it constantly emits a stream of charged particles we call the solar wind. And when those particles get wild, like during a solar storm, sometimes called a coronal mass ejection, or CME, they can slam into Earth's magnetic field with intense results. This is what we call space weather, and it is a real threat. Strong solar flares and coronal mass ejections can scramble communication systems, damage satellites, knock out power grids, and even endanger astronauts in space. Punch aims to give us the ability to predict these events before they happen by watching the solar wind form at its source. Now let's talk about the science and the reason NASA built Punch. To understand how the sun's atmosphere becomes the solar wind, we first need to understand the layers of the sun. The corona is the sun's outer atmosphere, and although it's very low density, it reaches temperatures of over 1,000,000 degrees Celsius, much hotter than the surface of the sun. That's another one of the solar physics' biggest mysteries, known as the coronal heating problem. Let me know in the comments below if you want a video about the coronal heating problem. The corona is made up of ionized gas, also called plasma, which is so hot that the electrons aren't bound to the atom, and because of their high kinetic energy, even the sun's gravity can't hold on to it. This plasma escapes into space, creating the solar wind, a stream of charged particles composed mainly of electrons and protons that can travel up to speeds of 800 kilometers per second. But here's where it gets tricky. This transition from plasma in the corona to the solar wind is gradual, happening in a space of about 20 to 30 solar radii from the surface of the sun. That's where Punch comes in. Punch's instruments use a technique called polarimetry, which measures the polarization state of light, particularly its angle of rotation, which when analyzed, shows how light is scattered and polarized by particles in space. When sunlight hits electrons and protons in the corona or in the solar wind, that light gets scattered, and that scattered light is polarized. By measuring the degree and orientation of this polarization, scientists can determine how dense the plasma is, how fast it's moving, what direction it's flowing, and what shapes it's starting to form, like blobs, waves, or CMEs. This lets Punch track dynamic features like plasma bubbles, turbulence, shock waves, and magnetic field structures in 3D, all in a part of space that's been nearly invisible until now. Think of it like turning on night vision goggles for the sun's invisible wind. We're not just seeing light, we're reading the physics behind it. Now you might be wondering, if the solar wind's always flowing, why don't we just measure it here on Earth? Well, here's the problem. By the time the solar wind actually reaches Earth, it's changed. The plasma has spread out, mixed together, and lost a lot of the fine detail of how it formed. If we want to understand how solar wind forms, we have to see it before it evolves, closer to the sun. But that region is incredibly hard to study. And there's a few really good reasons for this. Number one, it's faint. The corona and solar wind are millions of times fainter than the solar disk. Trying to image them is like trying to take a picture of smoke next to a floodlight. Unless you can block out the light from the floodlight, you're not going to see the smoke. But just like during a full solar eclipse, if you can block out the light from the sun, the corona can be seen. Number two, Earth's atmosphere blocks the view. Ground-based observatories can't see the polarization of light from the corona effectively because of the atmosphere, and they're also limited to daylight windows, which is why we needed to have cameras in space. Reason number three, that middle zone is way too big for any one telescope. This area, about 1 to 45 solar radii, is too broad to capture in one image with the detail needed. Most solar missions either look really close in, like the Parker Solar Probe, or really far out, like SOHO. Punch fills that gap by using 4 satellites, one with a narrow field of view looking fairly close to the Sun, and 3 other satellites coordinated to have wider fields of view up to 45 degrees away from the Sun, and positioned so that we get the most complete picture of that middle zone as we can. Together they form a seamless panoramic picture of solar structures as they form, almost like stitching together a time-lapse of a hurricane forming from swirling winds. The fourth reason is data overload and precision timing. To image something as subtle as electron-scattered light, the sensors must be extremely sensitive, and the timing and positioning of the 4 satellites must be near perfect to produce usable 3D maps. It's like trying to get a 3D picture of a ripple in a pond using flying drones. The satellites need to be in perfect sync, constantly sending and receiving information and adjusting themselves so that they are perfectly in position. So yes, it's difficult, it's ambitious, but if it works, Punch will bolster our understanding of how the Sun breathes and how its breath envelops the entire solar system, creating the heliosphere. Let's bring it back home for a second. Accurate space weather forecasting isn't just cool science, it's a critical need. Airlines, GPS companies, military operations, satellite providers, and even utility companies all depend on having accurate space weather forecasting. Punch's ability to track solar events in real time means better warnings and more resilient systems, and a clearer understanding of how the Sun shapes our space environment, because space weather affects Earth's weather a lot more than most people realize. Most people just think about the UV, visible, and infrared radiation that comes from the Sun as affecting our weather. But the particles from space weather, especially the more intense events like CMEs, charge the ionosphere, leading to magnetic and electric disturbances that a growing number of space and weather experts can attest that they increase the intensity of storms on Earth, especially as Earth's magnetic field is weakening as we get closer and closer to a magnetic pole shift. Punch launched in March of 2025, and its mission will last at least 2 years. During that time, it'll take millions of images, track dozens of solar eruptions, and build the most complete picture of solar wind formation ever made. Having the Punch satellite data is like going from blurry radar images to high-definition weather forecasting, but for space weather. And while it may be a small fleet of tiny satellites, its impact will be massive. With Punch, we're not just looking at the Sun. We're coming to a better understanding of how the material in the corona can change and shape and form into that solar wind. If you enjoyed this video, I think you'd like this book. I have an affiliate link in the description below. I do get a small commission, but it doesn't cost you any extra. If you like hearing about the Sun, make sure to click into this video here about the Parker Solar Probe. And for more videos about the space and science and tech around us, make sure to like and subscribe, and remember, keep asking questions. I'll see you on the next video.